Okay, good afternoon, Sam.
Hey.
Okay, let's start because I was going to wait a little bit more for people to come, but I don't know if they want to join or not. So let's start the class. And the fact that I'm recording, I'll share it later on YouTube so they can follow up with the missed content whenever they join. All right, so let's go and work the funnel waiver problem. So basically, we had a frame, two beams, and this was friction here, and there was another friction here, contact friction, mu s, and I had a weight hanging in from here, M, and the lengths were given L, and the objective was find at this point A, find internal moment at A. And usually for every hard problem there is a very short answer usually, and this was one of the problems. So if we go ahead and write down all the equations, that means if I take two systems, that's the way I did it in the YouTube video. And if I draw a FED for that, write down all the equations, I'm gonna get 6 unknowns here, mg, the opposite of that. So 6 unknowns for 6 equations, and then you can, excuse me. Then you write down, all these 2 of 3 equations, 6 equations, 6 unknown, and then you can find all these 4 unknowns here that I'm check marking right now. And then you realize when you go to do the next step, which is cutting in the middle and find these 3 components, then you realize all equations, they cancel out, and then you end up with MA is equal to. Now, it's a simple solution for that. As I said before, for every hard problem, we usually have a fast solution. The solution for that is by just considering this system, okay? So if I take these 2 systems and consider only beam, the beam on the left, then I realize that I only have a system like this, 2 unknown here. And you know that from the vector static class, we can rotate these 2 unknowns. We can align it with the beam. So if that's my beam, I can also rotate this guy a little bit to the top right. So I can write it like that, my unknown. In fact, I could draw my FVD from the beginning like this, as you can see, okay? So what do you see here? You don't write the friction equation, don't bother with the system number 2 on the right, just taking the system on the left. Well, it's immediately apparent that this is what we call in the vector statics, and it was in the review videos that I posted last week. We call it 2-force member. 2-force member. What does it mean? That means that if you write, take any point, like here or here or here. If you write summation of, for example, I take this point here on the left. If I write, let's call this A. We already had A. Let's choose another label. Let's take this to be, for example, F, G, H, L, whatever label you want. So if you write summation of moment about point F is equal to 0, what do I get? I get moment come from this zero, which is already 0, 0. This goes through zero. So the moment coming from this guy is 0. That means if I consider that like f, it's going to be f times L is equal to 0. That means f is 0, right? And if f is 0, that means if you write summation of force in this direction, 0, that means this is also 0. So the only thing you have is two forces that are exactly equal in the opposite sign, and they're only in the axial direction. So that means my system, in fact, loading on him simply like this. So that's the reason we call it two force. You see here, two force member, because these two forces are perfectly aligned with the axis. They're equal and opposite. That means if this is, for example, F, let's call it N, because we already have F was vertical one. So if you call it N, you have the same thing in opposite direction on the other side of the beam. Okay? So that's two force member. And immediately, if I ask you what is the moment at this point, internal moment, then you could just say, well, if I cut it, I'm going to get something like that. N, M, N, V, and for the system on the right, I'm going to get N, V, and N this way, and another N. So no matter what that normal force is, the moment is 0. If you write the equation of point A and take this system on the left, you immediately realize M plus this is 0, moment come from this guy is 0, moment come from this guy is 0. So only M remains in the summation moment equation is equal to 0. So the internal moment is 0. Okay. Now I want you as a homework. You don't have to turn it in. I want you to consider this case that you have the same system. You have a spring. So you have a spring here that connect these two part of the frame, the beam on the left and the beam on the right. And let's also put a parameter K for a spring constant. And let's assume that the initial undeformed length was when the angle theta, this was theta, right? When the angle theta was, right? That means the current length from here to here, L spring, this length is the one that comes in the force in the spring, F is equal to K LS. With this assumption, now find the moment at point A. What is the internal moment at point A? Is it 0 or you don't get 0? Now, this is a very good homework to completely give you an idea of, what two forces are and how it can simplify your job. And you'll get a good jump start to get ready for this mechanics of material course that you are currently doing. Okay, any question? Okay, let's go to, let's just open up another slide. And now we want to talk about important topic, shear / normal force and / moment diagrams. So this is a very important thing. These three diagrams, let's label it 1, 2, 3. You all the time you see these three diagrams showing up in this course, the next course, structure analysis, and even machine design. Some of you guys are mechanical. You have a course called machine component design. Then you have to be able to draw the moment diagram. and shear diagram, these two, in order to analyze that component of machinery. So this is extremely important to learn. So I that's the reason I say you need to solve a lot of practice problem at home and watch the videos I post, watch it several times, try to solve it yourself. So what is a shear moment diagram? Complete shear, normal force, and moment diagram. So let me give you an idea of what this thing is. Let's say we only have a beam here, one end, you have a roller, one end is pinned, and then, for example, you have a 2K force right here in the middle, 2K, and from here to here is 1 meter. From here to here is 1 meter. Now let's say this is your system. Now let's pick some points here. Let's pick, for example, some labels. Let's say this is A. Pick another point here, B. Pick another point here, C. Pick another point here, D. 4 points. Now, the question is, what is the value of these three components: force, normal force, and bending moment or internal moment? What are the value of these three components at all points, A, B, C, D? So if you actually, we can make a little table. Okay, like this, shear, can do that. Shear, normal, and moment. And these points, let's call it A, B, C, D. Well, you know that right now we're dealing with a table. It's not just one information, it's several information. So if I want to do this, solve this kind of, I simply use the approach I introduced in the previous class. I just cut it at any of these points, right? I just cut it, and then first of all, before I cut it, I found the external reactions, right? And then after I found my external reaction, I first simply just cut it at different points, take the system, either the one on the left or the one on the right, and then write the equilibrium equation, then find this component. And then after I find a component, I simply fill out this table and put it here, okay? So let's do this. Realize it's gonna take a while. Now, before I solve it, as an engineer, we don't really want to spend such long time. You know, this problem is a sample problem. I just simply solve it for you, just to show you it takes some time. But as an engineer, we actually draw this trend, the trend of, you know, variation of shear. For example, consider the first column, the variation of shear force versus locations across the beam. We just want to see a drawing. We don't like to see a table, right? We want to just see a drawing, and then by just seeing a drawing, like a plot, shear versus different location in table. By just seeing the plot, we can simply see where the maximum happens, where the minimum happens, and at what location I have changing the sign and stuff like that. But before I do the drawing, let me complete this table, and then I use this table to my plot, right? So let's do that. Let's first find the external reactions. So if you draw FED, again, I'm going through those 5 steps. You're gonna get EY, 2K, AY, AX. Then you write summation moment with X0. That's gonna give you 2k times 1 plus dy times 2, 0. So dy is equal to 1k, and therefore ay is also 1k because summation of force in y0, that means ay plus dy minus 2k is 0. So ay is 2k minus dy, 2k minus 1k is 1k. And ax is also 0. Why? Force in action is okay. So let me go ahead and put it here, external force. So there is going to be a 1k here coming from this dy and 1k coming from ay and no ax. Now let's open up some space here. All right. I wish it had a bigger eraser, but that's okay. So now and let's first do point B. Okay. Let's do point B. So what I'm gonna do, I'm gonna just cut it at point B, and then you have one system on the left and one system on the right. So which one should I take? The system on the left, because you have only one force, right? So I do that. A, K, moment at B, shear force at B, and normal force at B. Okay, 3 combat at B and just 1K at point A. Now I can just write this equilibrium equation to see that NB is equal to 0, summation of force in X0. That would give me NB is equal to 0. Summation of moment about point B is equal to 0, will be plus N minus 1K times the distance. The distance is 0.5 because this point B is in the middle of this beam. So from here to here is 0.5, right? So positive MB, negative 1K times 0.5 is equal to 0. And also summation of force in Y0, that means that 1K positive negative VB is equal to 0. That MB is equal to 500 or 0.5K. Let's do 0.5K. Let's keep that K in, 0.5K positive. And VB is also positive 1K. Okay, and MB is equal to 0. So let's put it in a table. So at point B, my shear, so let's check mark it. I'm filling out this row. You see, the second point B, what do I have? My shear is positive 1K, positive. Look, sometimes we only talk about the magnitude, but sometimes the sign is important. So when you want to draw shear moment diagram, please consider the correct sign. I had a student just talking about magnitude because, you know, when it comes to the design, they say, well, it's just maximum matters. But for some problem, the sign is important. So please consider that sign here. So positive 1K for shear force, and moment is 0.5K positive. I don't put the positive here, but that means it's positive, and the normal force is 0, right? So I have finished one row. So let's go and do the same thing for A, right? So the thing is here, this is an important thing, because point A is a kind of like singular point. Why point A is a singular point? Can you tell me why A is singular? Let me clean up this space here. A is a singular point. Why? When we say A, we're talking about mathematically exact location at point A. Well, it's singular because you see that force 1K, the external reaction is passing exactly through A. So this is called mathematically singular problem. When you have problem like that, then you have to kind of like, you remember from calculus, we had limits, you know, if you have X, if you had X like here, and you had curve like that, and let's say this X was 1, and then we had 1 plus after the, and 1 minus just before that point. It's kind of like mathematical abstract constructs to handle that singularity. We can do exactly the same thing here. So for this, I'm going to cut, if I want to find this first row, the internal loading at point A, because A is a singular point. Why? Because the shear force is going through it. I am going to cut at A plus. In fact, talking here, let me put a plus. We're talking about just after point A, not point A, just after point A. So if I do that, if I cut just after point A, you know, basically you don't really see it here. It's like you cut at A, but when you zoom your system, you have something like that. You have a cut, and this is the actual exact mathematical A, and then this distance is basically epsilon, which goes to limit epsilon goes to 0, right? Now, if I want to draw FVD for that, I am going to have 1K at A, exact A, and then here you're going to have MA, NA, and VA. Note that because I take the system on the left, you see, because you're going to get system on the left again, and another system on the right, right? Because I have the system on the left, I actually have VA, look at the direction of VA, VA going down. If I had the system on the right like that, the VA would go up. NA opposite that, MA like that. This is a very important observation, because if you don't do that, you don't get exactly the same result if you choose the one on the left or the one on the right. Your result would be different. You have to be consistent with this notation that I said, that I show you here. So right now at point A, I have MA, NA, VA, and 1K, and that distance is epsilon. So what can I write here? Summation of force in X0, give me again NA 0. Summation of force in the Y direction, give me 1K plus minus VA is equal to 0. Summation of moment about point, let's say A, is 0. What do I get? MA, okay, positive. Negative 1K M is equal to 0. And don't forget that, see, limit when epsilon goes to 0. Don't forget that. When epsilon goes to 0, MA goes to 0 too, because MA is equal to 1K times epsilon. So MA is equal to 0. VA is equal to 1K positive, and NA is equal to 0. So let's put it back in the table. So the first row, let's get rid of this yellow line here. The first row, I'm gonna get rid of this stuff here. Okay, I'm going to put NA, the normal force 0, the shear force is 1K, and the moment is 0. Now let's go to point C. Again, we have a very similar procedure. Clean up space here. All right, at point C, I need to cut it. What part should I take as my system? The one on the left or the one on the right? Which one do you recommend? Let's cut it at point C. So I'm gonna get system 1 on the left, system 2 right. Which one should I take?
The one on the right.
The one on the right. The one on the right only has one force. And again, as a homework, you don't need to turn it in. Do the one on the left, and you should get exactly the same thing I get from the one on the right now. So if I cut the system on the right, system 2, I'm going to get, this is point D. You are, okay, go this way. Then M at point C, N at C, and V go up at C, NC, VC, MC, 1K, and this distance is 0.5 from here to here, 0.5 meters. Now let's go write the equation, equilibrium equation. You get NC is equal to 0, VC is equal to negative 1K, and MC is equal to 1K times half, which is 0.5K. I just simply made a shortcut. So if you expand the force in X0, you get NC0, then you summation of force in Y, VC plus 1K0, then you solve for VC, you get VC negative 1K. Summation of moment was C0, then you get negative MC plus 1K times 0.50, so MC is equal to plus 1K times 5.5. So let's put it back in the system. So at point C, I do get here is shear force negative 1K, normal force 0, and moment 0.5K. Now we go point D. What do I get at point D? Well, you already did point A. Now point D should be very easy. We just cut it. Point D, we cannot do exactly at point D because that's a singular point. So what I do, I just cut it. Let's open up, clean this blue lines here. It could be very misleading. Okay, so I just cut it at D, but if I zoom on it, I'm gonna get something like this. This is your actual cut from here to here is epsilon, and 1K at exact point D. This is your D. We're talking MD, VD, and ND, VD, ND, MD, and all those things. So if I solve the equation, I realize VD plus 1K 0, so VD is negative 1K, the normal force is 0, and the bending moment is what? I'm waiting on your response. The bending moment is equal to?
0.
0. Thank you, Sam. So that's it. I got my table. Look, here, just for the purpose of, you know, because I'm going to use that table to draw my curves, you know, exactly like the way you do in Excel. You know, you have 2 columns and then you just select the area and, you know, you can draw a curve. That's what we're going to do right now. So before I do that, let me add another point to this table. This table, let's add another row to this table, and let's call point B, C, D, E, point E, and let's say this point E is exactly in the middle. Okay, so I want to find these components at point exactly in the middle, E, right? So tell me, what is the point E? Is it a normal point or singular point? According to the definition of singularity, it had a point load or point moment, you know, couple moment, like 2 kiloton Newton times meter. If we had a point load or point couple moment passing through a point, that point was singular. So this point is also singular. So I cannot call it exactly at E. So let's call it at E minus, just before E. Let's have more point. E plus just after point E. Okay? So if I cut it at E minus, what do I get? I get, so I'm cutting it just before point E, right? I get something like that. So this is 1K going up. At E, I have ME, VE, and E. And this is minus, E minus. Moment at E minus, the normal force at E minus, and the shear force at E minus, right? And this distance obviously is 1 meter from here to here. But look, 1 meter is from A to E. So what would be this distance from A, point A to this point is E minus? What would be that distance? I'm waiting on your response.
One minus E.
Exactly, 1 minus epsilon. Okay. It's 1 minus epsilon. So if you write the equations, summation of in y 0 gives you V E minus is equal to positive 1K. You get that N E minus is equal to 0, summation of force in x0, right? And then you get M E minus is equal to what? Is equal to 1. My shear load is plus, this important thing, look, plus 1K, right? And the normal force 0. And you may see, well, we always get 0 for normal force. So what am I just putting in table? I can just eliminate it, and that's right. But look, sometimes we don't get normal force is equals to 0. So we have to plot that diagram too, right? So that's the reason I just want to be comprehensive. So that's the way I include it here. And then the moment at that point is equal to ME minus is equal to 1K, right? So let's go to E plus. Let's go to E plus. What do I get? If I want to do E plus, again, I have to do another fresh cut, right? I cannot use this one because this is cut at point E minus. So I do a fresh cut like that, right? And then I take the system on the right because I only have one force, okay? Then at this point, E plus, I'm going to get ME plus, VE plus, NE plus normal force, shear load, moment at point E plus. And 1K, and this distance is, again, 1 minus epsilon. And don't forget, epsilon goes to 0 in the limit, right? So if I write the equation, what do I get? I get shear load, look at negative 1K right? The moment is positive, let's use black. So this is negative 1K. The normal force is 0, and the moment is still positive 1K. So look, when we pass through this discontinuity at the point E, you see in the middle, because I have a shear load, I'm gonna get a jump in the shear distribution, or we call it diagram, right? You see it goes from plus 1K to negative 1K. That's the reason I call this point is singularity, because you get some sort of jump in your diagram. But look, there is no singularity in the moment and no singularity in the normal force. That's interesting, but it's singularity in the shear. So that point is singular because one of these physical parameter is discontinuous there, okay? So now let's go ahead and get plot out of this, table that I created. So if I want to do a plot, usually the way we do that is we just draw it along this system. So I'm gonna extend this line. So I'm gonna have 3 plots. So this is your X location in, let's call it meters. And then one of its axes is the shear, or we can just call it normal force. The other one, again, X is your shear. And the last one, X, is your bending, internal bending moment, right? And then the way we do that, consider this point just extended. We just draw it proportional to this elongated lines. So we get a plot that is matching our system. Okay, so we can quickly analyze what's going on here. Where is the maximum shear? Where is the maximum moment? So let's do that. If I plot that for, let's first do N, the easiest one. N is always 0, regardless. So your normal force is always 0, regardless where you are, right? So look at the table, the middle column, the normal force is 0. So I get plot like that. What about shear? The shear, if you are before point E, you see, if you are A or B or E minus, in all cases, your shear is positive 1K. And just, excuse me, excuse me, this point is singularity, so it doesn't exist. You have a empty circle here, and just after this point, then you get negative 1K. Negative 1K. 1K negative. That's your shear diagram. So the one on the top, they call it normal force or axial load diagram. Okay, they also call this normal force axial load diagram. The one in the middle, they call it shear force diagram. And now let's draw the moment diagram. Usually the most important one is the moment diagram. And I'll tell you why the moment is most important, because the beam deflection equation, in order to do deflection analysis, you have to have the moment diagram before you start doing deflection analysis. So if I want to draw the moment diagram, I just simply connect these dots. At A, my moment is 0. Look at the table. Moment at A is 0. What's the moment at point B? 0.5. What's the moment at point E? Positive 1K. E minus. What about E plus? It's still positive 1K. So I'm right here. Then you go point C, 0.5. And then you go to point D, which moment is 0. I'm circling it. There you go. Then connect these dots together. Then you get this diagram. That's your moment diagram. It's like a triangle. So if I show you, you see right now we spend like about 30 minutes more, 35 minutes, just draw these diagrams. Now I tell you, when you go work at a company or a school or whatever, there are softwares that you can use that when you give them the structure, they're going to immediately give you a shear moment diagram. You don't really need to draw it every single time. But you have to know the under the hood, how those plots are obtained in order to be able to use it and verify it. That's the reason we're teaching it. Otherwise, if you really want to draw this thing, you can use a software, draw this, your system, just put the loading on and then tell a software, give me shear moment diagrams, and it's going to plot it right away in less than like a second, okay? So right now, if I ask you where my maximum moment happens, is the answer? Well, if you have this little table right here, look at the table, and let's say you have a table is obtained for like 200 points across this beam. Then you have to go through all these 200 rows to get the maximum for moment, max for moment, right? And that procedure is very time consuming. You don't want to do that. But what's the advantage of plots? The advantage of plot here is I get this case. I say, well, the maximum happens exactly in the middle. Why are we talking about minimum maximum? Can you tell me? Why are we interested in to find a minimum maximum for shear and moment? I'm waiting on your response. We are, let's see who is in the room. We actually do the maximum analysis for design. Max values are used for design, and you can design, and you can see that when if you want to do something, what's the maximum possible load on this part, right? And then you choose a thickness or property of that material or your design such that it can accept that kind of loading. So that's the reason we're talking about this maximum points here. In the next sections of the course, we have those maximums and we use something called safety factor, and we do some preliminary design. So now let's go to another example. Now this one, I want you guys to draw the shear moment and bending diagram, these three diagrams, and I want you to send it to me. So let's make another slide. Right here, let's do this. This is wall. Let's see, you have a force here, 1K, and a couple moment, 3 kilonewton meter, and there's 1 kilonewton, and from here to here is 1 meter. From here to here is 1 meter. Now the question is, draw moment slash moment diagrams. That's the question. And I didn't say normal force diagram. Why? Because normal force is 0. We don't have axial load here in this problem. So go ahead and work on this problem. And let's assign 10 minutes. So 159, let's say 2. By 2, please submit your work to me. I just want to see how you work on it. I mean, you don't have to do it correctly. I just want to see how you do it. Okay, so please email me, and in order to send it, simply email to this email address. @utc.edu. Scan your paper, take a picture, and email it to this. You do is you introduce some point, let's say this A, put a point in the middle of here, B, and C, put another point D, and E. And you know that, well, E is, for example, point E is singular point because you have 1K load passing through E. So you have to take E minus, you know, things like that. Or point C, you take C minus, C plus. And eventually, if you do it 3 times, you realize, well, it's easy. You just simply don't say plus or minus. You can determine which one is positive, which one is negative. So the first thing you do, find the table, do this table. With point A, B, C, D, E. And exactly the thing that we did before. Then you have shear and bending moment. So you're gonna fill out this table. Okay, once you get the table, we simply, so this is step 1. Step 2, you simply plot X, whatever parameter you have, shear / moment. Okay. Well, let me on this. Let's working, clean up some space. So right now, the first thing I do, I want to find the external reactions. So that's my FVD. I take the entire thing in system 1K, 3K, and AY Well, I don't simply put AX because I know 0. You're trying. Then you write the equation, you get summation of force in Y, AY, negative 1K is equal to 0. Summation of moment about A0, you get MA positive, negative 3K, negative 1K times 2 equal to 0. So you solve for that. AY is equal to 1K and MA is equal to 3K, negative 2K, negative 5K, take it to right, positive 5 kilonewton meter. Newton. So just let's put these reactions here. At AY, you have 1K, 1K, and then you're going to get the external bending moment or couple moment, 5K. At A, get rid of this computation, no problem, some space. Now I draw my table. Let's put shear. Need to use black color. All right, shear moment. Only 2 column. Then you're gonna get point A, B, C, D, E. A, C, D, E. And right now we're trying to fill out this table and then use that to draw. So at point A, again, if I do cut at E, A plus, then I get cut epsilon. That's going to be MA, VA. I don't put NA because it's always 0. You can see that. So VA, MA, and that distance is epsilon, and then you're going to get this actual A, that's A plus. And these are plus, don't forget that. And this actual A that you have 1K upward and 1K this way. So let's put this bending moment direction should be this way, 1K counterclockwise and 1K positive upward. And then the shear force is down positive, VA plus, MA plus, and no axial load. So that's what you get at point A. So if we write summation of force in Y, in this table, the shear becomes positive 1K. And the moment becomes, what's the moment at A? The moment at point A plus is equal to 0. You get MA plus, right? VA plus pass through that, so there is no moment. Then you get negative 1K times epsilon plus 1K. This 1K is just already the wall bending moment. So you just simply add it to the moment equation. Is equal to 0. So your MA plus, in fact, is 1K times epsilon minus 1K. Right? When it goes to point A plus with A become the same to remove the singularity. So your MA plus become 1 kilonewton meter with negative sign, right? So let's put 1K here, negative 1K, and get rid of this system. What about point B? Well, point B, you don't have singularity, so it's easy. Just cut it, take the system on the left. B, so you have VB, MB, and there you go, you have 1K, 5K. Okay. Hold on. I put in the previous calculation, I think I should have used 5K, negative 5K. Look, let's do it again. I thought this was 1. So if I A plus, this is epsilon, VA plus, MA plus, and this point 1K, positive, and they're going to be 5K. I thought it was 1K, positive 5K external, right? So yes, VA plus or V becomes positive 1K, or same for 0, so VA plus minus 1K is equal to 0. That means VA plus is equal to positive 1K, and you see here in the table. But for moment, summation of moment about A plus 0, then you get MA plus, okay, nothing from VA plus, and then negative 1K times epsilon plus 5K. Last time I put plus 1K, is plus K 0. This becomes 0, so MA is negative 5K. MA plus, MA is negative 5K, so negative 5K, not negative 1K. Sometimes we do mistakes. All right, so point B, again, point B is easy because we don't have singularity there. Point B, right here, 1K, 5K at A. At B, I'm going to have MB, VB, I don't even put NB because it's 0, VB, MB, and 1K, 5K, and this is 0.5 meters, 0.5. Again, write the equations. Then you see VB is positive 1K, 1K, 1K negative, VB is equal to 0. VB is 1K positive. And if you write moment about B is 0, summation moment about point B 0, then you get MB positive negative 1K times 0.5 plus 5 times 1K is equal to 0. Go to 0. Let's write it here down. It's gonna make a mess here. So summation of moment about point B 0. That's gonna give you MB positive negative 1K times 0.5 plus 5K equal to 0. So that means that see MB negative 1K times 0.5 plus 5K 0. That means that 5 minus 0.5, 4.5, take it to the right, MB becomes negative 4.5K. Okay, 5 minus half is equal to 4.5, take it to the right, negative 4.5K. So let's put it here, negative 4.5K. Now let's go to point C. Again, if I go to point C, because it's singular, you see, this time singularity is in the moment diagram, because at point C we have a couple moment passing through the C. So the singularity is in moment, not shear. Okay, so I just take just epsilon before C. So I'm talking about C minus. Let's put here the point that we consider is just before that, C minus. Okay, if I do that, then I'm going to get is 1K, 5K, and here this length is 1 minus epsilon. And then here I'm going to get MC, VC, and no NC, NC 0. So that's my FED. Excuse me. If I write the equations, I get VC plus 1K equal to 0. So VC is 1K. So the shear load is 1K. Excuse me. The shear load is 1K. And then I go to moment equation, summation of moment. Point C is equal to 0. Then I get MC plus 5K negative 1K times Epsilon is equal to 0. Excuse me. MC, that's 0, negative 1K times 1 minus epsilon plus 5K is equal to 0. When epsilon goes to 0, you get 5 minus 1, 4, take it right, MC become negative 4K. So here, negative 4K at this point. Now let's go point D. Point D. You simply cut it at D. Now the question is, should I take the system on the left or the system on the right? Well, I don't ask you because you know the answer. The system on the right makes your life easier. 1K. Don't forget, when you put MD this way, VD go up with the system on the right. Don't forget that. That makes a big difference. And ND is simply 0. So that's your FED for the system on the right. And don't forget, from here to here is 0.5 meter. If you write the equations, you get VD minus 1K is equal to 0. VD is equal to positive 1K. And moment about point D gives you MD negative, no VD, because it's passed through point D. So negative MD, negative 1K times 0.5 meter is equal to 0. That means your MD is equal to negative 0.5 K. So 1K times 0.5, and it's negative. You take it to right, negative 0.5 K. All right. So let's put it in the table. So V is still VD positive 1K. The shear load is positive, and MD is equal to negative 0.5 K. Okay. Then now you go to point E. Now point E, for point E, let's see, I'll just simply cut it at E minus just before E, right? We don't have E plus. E plus is outside of the beam. So I just simply cut it just before E. And then I have, let's zoom on it. So if you take that and zoom, then you have, this is epsilon. And then you're gonna have already 1K. This exact point E and E minus. And then E minus, you're gonna get ME minus VE minus, no axial load. So if you write the equation, what do you get? You get shear load is still positive 1K, and the bending moment is equal to 0. You see that? Because you have ME minus epsilon times 1K. This is a moment coming from this with respect to point E minus is equal to when epsilon 0 become what? 0. So that's your data. So let's plot it. So if I want to plot it, okay, we're getting close to 2:15. We were planning to finish this class by 2:15, but I think it's going to be like 2:25 because the plotting takes some time. So if I want to plot it, again, I use the same proportion on my beam. I just light these points like that. And I put my x-axis like that in meters, location, different points of beam. One for shear. So one plot for shear, one plot for moment. Okay, we can put these two plots in separate papers, separate pages, but it's always better put in the same location that your beam is, so you can see at what point your maximum happens. So you can correlate those points with the location, the graphical location on the beam. So it's always better to plot it just on the beam, like the way I do it here, okay? So if you go to the table at point A, the shear, as you can see, the shear load is always positive 1K. So you have a constant positive 1K from beginning to the end, positive 1K. That's your shear diagram. Now, what about the moment diagram? Well, the moment diagram, you have kind of like here, you have -5. It's a line, two lines actually, two segments. And then negative line with a constant slope goes to point C, which is -4. So you don't have that much change here. That's 4, -4K. So you have a line with a moderate small slope like that. And then you go from -4 to -0.5 and then 0. Then you have a line with larger slope, right? So that's your bending moment diagram, two line segments. You see? And the thing is, at this point, if you plot, let's do that. Let's before we plot that, let's plot this at point C. You see, we only had at point C, we had C minus. You see here, let me circulate this thing that we did C minus. Now, if we do C plus just after, I'm gonna get something like this. This distance is 1 minus epsilon 1K, and this point is C plus. Just after that, MC plus VC plus going up because it's on the right. So then if I write moment, then I realize moment becomes -1K. So the moment starts from here. So we continue. And then -½ and 0. That's it. So you're gonna get two line segments that you have a discontinuity at point C on your moment diagram. But look, the shear diagram is continuous. You see here, this point C. C plus, C minus before, and this point C. All the same, 1K. No discontinuity. But here, diagram is discontinuity. Can you tell me why we have discontinuity in the moment diagram, not shear diagram? Let's say one quiz bonus. One quiz bonus. Only one person get it. The first person says it. Can you tell me why we have discontinuity in the moment diagram, not the shear diagram?
Is it because there's an applied external moment?
Exactly. Because the answer is because applied look at, let me bold it here, 3K. So it's because external couple moment, you have discontinuity in the moment diagram. Now what happens if there was external, instead of couple moment, there was external shear load? Then what do I get? Discontinuity in shear diagram, not the moment diagram, right? I get the discontinuity in shear diagram. So this is very important. Whenever you have a point load moment, you have to go to your diagram and see a discontinuity in either shear or moment diagram respectively, right? You have to go and check it because otherwise your diagram becomes wrong. So this is for today. I'm going to put more slides. I'm going to put more YouTube videos. I'll put a link on YouTube. Also, you can subscribe to that YouTube channel that I have, because if I upload video notification from YouTube, which are more reliable than notification from Canvas. So I'm going to put more videos for these shear moment diagrams. And now let's finish up this class, the lecture class, mechanics of material. Any question? Before I go to the mechanics of material lab, the lab class. Any question? Okay, let's start on the lab. Okay, last thing we talked in the lab lecture was a spring constant, and we realized that everything in a mechanical system can be replaced. So this is your complicated system. Let's draw a fairly complicated system. And then you got some spring loading here. And then there is another truss here. And one hanging weight here. So if I put a load here at this point, let's say, for example, right here, if I put a load here, this system is going to undergo some sort of displacement like this. Let me draw the displaced system like that. This kind of like displaced system that has some displacement now. System moves, and this point, original point, you have some sort of displacement with delta. You see, it goes down a little bit, delta, then you can always F is equal to the spring constant times delta. So it doesn't matter if you have just simple spring or a very complicated mechanical system like the one that I plot, you can always replace this entire thing. You see that? You can grab this, replace it with a single equivalent spring. And this is load F and grounded. So in order these two systems become equal, you have to have the spring constant of two systems matching, right? So you can replace one with the other. And that's what we talked previously. and we derive some spring constant. One was AE over L, K, and then we talked about delta K over K using two different, one was, I'm just trying to give you a recap of what we have done last class, high-low method, and then the other one was partial derivative method. And then I said, go to your lab manual, the first one, and just do these two things to validate the formula. There was a formula for delta K over K, and you need to do partial method to validate that. Or you could use high-low method to validate that, starting from scratch. So we talked about this, and now I want to go to the to that little table. You remember we talked about table. Let's put it here. This table, we had several columns here. One was delta K over K. One was just a spring constant. There was no delta. One was simply K predicted. And the second column was delta K over K predicted. So we already did that in the previous class. And the predicted, we means use formula, because it's theory, the prediction. Then we saw there was something called K0 and delta K over K observed. And then there was a relative error, and there was finally a max error. So this is my complete table. Every single lab I do, I have to report this table and then answer the question. This is the first thing comes in the report, okay? So what are these two columns? Let's talk about that, right? Let's see who is present in the class. I know that some of you people have difficulty with the rain, but the thunderstorm, and but looks like everybody's here. I'm glad. Okay, so now let's talk about these two columns, K observed and delta K over K observed. So another slide. Need to open up one more slide. So hey, you remember we had a cylinder with length L and cross-section area A and shear and Young module of elasticity E, okay? And we said if this thing is under loading F, it's going to extend a little bit. It's going to first shrink and extend like that. And this, let's call it delta. And we realize that the spring constant for that, if you write the equation, becomes sigma. We'll talk about this. You don't need to know this. I'll talk about this later in the next class, the Mechanics of Material Lab lecture, the lecture class. The stress at points is equal to E epsilon. The stress is F over A equal to E delta over initial length. And wrote this equation in term similar to F is equal to K delta to realize that F is equal to AE over L, and that's my K times delta, okay? So what this equation is telling me that is when you increase the force, the relation between force and deflection is a linear relation, right? So this is all theory, this is prediction. You see when you say K predicted, this usually K predicted. Now, predicted, now the question is, how can I measure this? Because, as an engineer, you should not believe any predicted equation. You shouldn't have trust in any like formula. You should just, as an engineer, you should see whether I should see it myself or I should validate it myself. Now the question is, how can you validate this by using lab equipment? Can you answer that? That if I give you a bar like this in the lab and I say, find this K using the equipment we have in the lab. We have a tensile stress machine. We put it in the machine, apply tensile load. Now the question is, how do you validate this K? Can you answer that? Well, let's say this is your machine. You have two jaws here, jogs. This goes up, so it's kind of like machine like that. It's flexible. It goes up and one on the bottom. It goes, so here, let's say put a hook here and one on the bottom. Also can move like that. So this can go up and this can go down, right? This goes down and this goes up. So what I do, and there is another hook here. What I do, I grab this bar or my specimen and I just fix it right here. You see that? And then I apply load. So I tell this machine to go up a little bit, like step by step, every 1 meter. So the initial displacement is 0. And then I tell the machine to go up 1 millimeter. And then I measure the force here in this bar, force. So I have a machine, a transducer that has force measure transducer here. And it tells me what value of force here, right, in this bar. So I just plot it. Force in the bar versus displacement. First point is right here, because if I don't have any displacement, right, the machine does not give me a value for force. It just give me like 0.1 Newton, and then it changes 0.2 Newton, and then it goes to 0.01 Newton, and then changes 0.05 Newton. It's like a random noise, right? It goes up or down, but it's about it's about 0 Newton. It's somewhere here, right? In the measurement, everything is completely, you have always this kind of random noise all the time. You cannot get rid of this noise in the measurement world. Not in theory. So now I increase this displacement here. So I tell the machine, go to this upper and lower jog to go up and have a displacement of 1 millimeter. Then I measure the force in this, for example, bar. The force comes, let's give some value like 10 Newton. So let's say this 10, 20, 30, 40, okay? Equally spaced. So if I get the first one is right here, 10 Newton. Now, if I increase 1 millimeter further from the 10 Newton point, I get like a point like here. It's not 20, let's say 18. So this is 10, 18, right? And if I continue, so if I go 1 millimeter, these are 1 millimeter increments. So what I get a bunch of data like here, here, let's put it here, bunch of data that are not exactly on a line. It's not exactly on a line, they're close. Let's put a value here, 35, here, 30, and then here, 41. So that's what you get from the machine, right? So you tell me, what do I expect if I want in the theory, if I want to draw force versus deflection, F in theory, what is that curve? Force versus deflection. Look at this equation. What is that curve? Waiting on your response. In the theory, what is that curve? Force versus, yeah? It's a line, right? It's a line that always passes through 0, 0 exactly. So this is like exact intercept with 0. And it has a slope called K, right? And this is K theory, right? Right here. You see that? But look, in the actual measurement world, these points right here, these my points, they're not on a line. You can see that. They're kind of like distributed. They're not on an exact line. So what should I do in order to get a relation between F, the vertical axis, and the delta axis? What should I do? Waiting on your response. Any idea? Well, have you heard the regression analysis? That if you have a bunch of scattered data, you can always do regression analysis. Have you heard it or not? I want to get the feedback. Please go in the chat room and see. I want to see how many didn't even have this regression, so I can talk about it a little further. Let's see. Okay. Now, do you hear me? For some reason, I just muted this sound here. Okay, yeah. So basically, I heard that, yes, all of you guys said you didn't have regression analysis, and that's just fine. It's not hard to do regression analysis. So I just said that if you just consider the curve on the right, you see, because all the points are exactly clustered on the line, you see this red dot, red cross point are exact on the line. You can always get the exact line that has theoretical slope k, so that's k theory. But in the measurement world, these points are never on the line. That's the problem. Because of the measurement error, because of the noise, because of the nonlinear nature of the material, because of a lot of problems, as you can see, they're not on the line. So the concept of regression analysis is that you put this point on a line that is as close as possible to all points simultaneously. So this problem is mathematically defined as regression problem. So the objective of regression problem is find a line that is close to all points as much as possible. And as you can see, I draw a yellow line here that is close to all the points here. And it doesn't necessarily go through 0, 0. You see, it has some drift, but it's close to all points as much as possible. Because sometimes you cannot get that line close to all points there. If your points are so deviated, for example, you have a bunch of points like this, you see? And then if you fit a line to the center, some points are very far, far away from the center line. But in this that we have, for example, in the example that we have, the data are not that much deviated. So this line is a good, accurate fit. They call this line the regression line. And you don't need to worry because Microsoft Excel or MATLAB will give you the slope of this curve. Okay? Observed. Because, look, because this line comes away, you see all these points, we got it from the machine on the right. So the slope of this is a spring constant, right? But is a K a spring constant? Observed, because it comes from observation. It doesn't come from the formula, right? We didn't use AE over L in this case. We use data from the machine, and then we fit a line to it, this line, and the slope of that is K observed. Now you can go back to the previous table. This line, this column right here, you need to have the measurement data, okay? And you need to put the measurement data in one of these software like Microsoft Excel or MATLAB. You need to put in one of the software and tell it, fit a line and give me the slope of the line. And now look, if your measurement is good, these two columns, K predicted, should be close to that. They should match. They should match pretty well. You never get exactly the same answer. For example, if you get 12.1 here, you may get 11.8. It's going to be close, but it's not exactly the same because of the errors. Now that's one of the questions in the when you write your report, you have to answer the question why you didn't get exactly the same. What was the source of error? Okay. So now I want to give you a hands-on. So let's go to this problem, and we want to do it together. Use this data, use either MATLAB or Microsoft Excel. So use one of these software, do this regression analysis, and tell me what a slope you get. So this is your x data, y data. So my x was 1, 2, you see 1 millimeter, this is a millimeter, right? 1, 2, 3, 4, 5 in this particular example, and the y is 0, 10, 18, 35, 41. So open up either, how many of you guys do Excel? I want to get feedback. If you just do Excel, we just do it in Excel, we don't do MATLAB. Let's get a feedback here. How many good you guys do Excel? You remember I sent an email last night that you need to install one of these software on your computer. So when you do regression analysis, it gives you the slope of this fitted line. You can simply put it in the chat room. Tell me how many of you do Microsoft Excel. I didn't get any response yet. Okay, because I didn't get any response, I just assumed that you all do it in Excel, okay? So if I want to do it in Excel, all you need to do is to put this first column in the, you open up a new spreadsheet and then you put this column and then the second column, and then you select these two columns and say insert the plot, okay? So it's gonna make a scatter, and when you say insert plot, insert plot, and then it's gonna give you scattered. You select a scatter plot. So basically what it does is gonna plot this scatter plot with the blue lines here. You see blue line, blue symbols with the blue symbols. And then you say, right click on it and say, add a trend line. And in the trend line, you say, select linear regression. And then there is a property right there. You right click on it and say, show me the equations, right? So what it does is going to add this curve. This curve needs some computation. So Microsoft Excel is going to do those computation. It's going to compute this curve, slope of it. Let's say this, for example, whatever it is. Then it's going to write it down here. The slope times x plus b. That's your y. This is the one you use when you write your report. This is the one you use in this column. K observed, right? So how do you find delta K over K observed? Well, you go back to your plot. Here, you eliminate, you want to see the sensitivity of your slope. So what you do, you just eliminate some of these. For example, I only consider 2 points, right? So I eliminate this point, this point, this point, and this point. And I only have two points here. Hold on, where is undo? Only consider 2 points, right? Eliminate, no, undo. Just the blue one. Okay. Just consider 2 points. Now fit a new curve to that. So again, you go to the regression and just say fit to a curve to this only 2 points. So you get another line. You see that? Like that. So the slope of this, you say K observed, but for 20% of your data. The first curve, 100%, you use all the points to get the slope. Here, you eliminate all the points except 2 points, which is usually the worst case scenario, the points that are far, far away from the actual line. You pick those, you feed a new line, you can get K 20%. And then you come to the table and say delta K is K, delta K observed, delta K observed is K 100% minus K 20%. Absolute value. That's your delta K observed. And when you divide it by K observed, that means delta K observed over K observed is the same fraction divided by K original, all the point 100%. And you just put the value right here. And this value should be small. As long as your data are in this very good on the line, this value should be small. If your data are deviated from that line, it gets, right? So we talked about the first column, second, third, fourth, and now the fifth column. What is relative errors? Relative error is the difference between K predicted minus K observed divided by K predicted times 100. Don't forget the absolute value. So it's a relative difference between the predicted spring constant and the observed spring constant. Right, so it's a very easy thing. As long as you have these two values right here, sorry, as long as you have values right here, this column and this column, you simply subtract divided by K predicted times 100. That's your relative error. And what is max error? Max error, this last column, let's write it here. Max error is absolute value of delta K over K predicted plus delta K over K observed times 100. Max error. Okay, so now we finish the table. Now it comes to the validation. There's always a question in your report that you should answer, that if you have validated this lab or no, yes or no. It's kind of like yes or no answer. And if you don't validate it, then you have to explain what was the source of error that you could not validate it. So when do we say we validated the theory? That means the K predictor is a good match with K observed. Well, here is the thing. If, let's write it here. If the max error last column, max error, and relative error don't forget this is the and, both of them are less than or equal 20%. So if your both errors are less than 20% or equal to 20%, then you validate, right? You validated this. That means your theory is in good agreement with your measurement, right? If this condition is not valid, then you did not validate it. So you have to explain why you didn't validate it. What was the source of problem? And look, I'm not gonna grade your report based on if you validated, going to grade based on if you have followed the right derivations. Like if you have done your partial derivative method correctly and you report the answer, even if you don't validate, let's say you get 80%, right? For your computation, this becomes 80%. So 80% obviously is not less than 20%. So you did not validate it. So you have 80% error. That doesn't mean that you get a bad grade, as long as you explain what 80% happened. What was the source of problems? Again, I'll look you, I'll check your derivation and stuff like that. And if everything is right and your explanation is right, you get a perfect grade. Okay? So this is all we have in this lab. And I think I've explained, I've covered all part of, including report writing, error analysis, how to fill out this table, answer the question. And now I'm waiting on you. If you have any question, then we can discuss it. Otherwise, we can finish this class.
I had a question.
Yes.
I'm still confused a little bit about where we get each value from. Like, there's the Excel file for the Spring Lab, and on the second page, there's a table that looks the exact same, right? But those are not the values that we use, right?
Let's go to let's go to the actual data on the website so you can show me what part you're talking about. So let me switch to the, let's see if I can share my screen. Okay. Let's go share screen, Zoom. Start board there. Okay. I'm sharing the screen. Let's see. Mechanics of material. Dashboard. Mechanics of material. Lab. Then we go here. Spring constant. Okay. So do you see my screen?
Yes.
Okay. So this part is just simply the theory that you just read to get equation for a spring constant. If it's not here, the equation is just given to you. If it's not given, just substitute equation to get it. And then it's come to the measurement procedure and, you know, the type of report you write, lab report, and this is the template. So what you say is this curve in your lab report is not equal to the data sheet that the Excel sheet that I provided to you. Is that right?
I'm not sure. I opened the Excel file and it has that graph on the second page.
Okay. You're talking about this graph right here?
Yes.
Okay. Well, sometimes this graph, you see, this is like a dummy graph here. It's just to show you it's like a placeholder. It's just to show you where to put the graph here. And you see, you should not use this graph right away. You have to go through the Excel file and use the data file. So let me go through the Excel file, the previous file here. Not that. See the Excel file. So here, you see this table right here? This is the data, observed force versus displacement. You see, I'm talking about this table right here. That's the data you should use. So you have to copy that data in a new Excel sheet and fit the regression line, get the slope. Here in this example, the slope becomes 3.4492. But you have to do it yourself. And then you go back, when you get that curve plot, then you put it right here. Let's go back here. Previous. In your report. Is that the answer to your question?
Yeah. So I still don't understand where you get K predicted from. So, because I thought you said that was K observed. You get that.
That's observed, right? K predicted is this equation you see right here. This is K because this is just, it's like prediction. You don't do any observation, right? You just use this equation. This is your K predicted. But what you need to substitute in this equation is mean value for G, mean value for D, mean value for capital D, and mean value for number of terms. And these mean values are also given in the Excel file. Let's go to the Excel file. No, that's not it. There you go. You see his measurement, the person who did that, for example, mean value for capital D is 10. Mean value for lowercase d is 1.35. Mean value for number of terms is 9.5. You see? And also he gives you the error. So it gives you mean values and deltas. So that's what you use. The mean value, you put it in that equation that I'll show it to you. That gives you K theory. Is completely theory, it's just a formula. This one, the slope of this curve is K observed because you do measurement, you feed the regression. So it's observation, the spring constant. Now, did it answer the question?
Yes. And then,
okay.
So for delta K over K predicted, we can use either the high-low or the derivative method?
Yeah.
Okay.
That's right. But in this lab, I recommend to use both of them. And I know you have done it, both of them, but for like every other students, every have to use both of them. But for the next labs, it's just your choice.
Okay.
Except when you cannot find maximum minimum easily. For example, when we have torsion, which is MLB. In MLB, you have to use partial derivative method. You cannot use high-low. You have to use partial derivative method. Because equation is complicated and you cannot see the maximum minimum easily. Okay? All right, what else?
So basically the only thing that we're using from the Excel file are these tables in green.
Yeah, you just simply use the table of measurement from the Excel file. And you know, if we had access to the lab, we could just do this measurement ourselves. So I would give you a caliper to measure different parts and find the deltas. You remember max minus mean divided by 2, and mean, like that. Because we don't have access to the lab, there is no way except I provide you this measurement from the previous students. That's the only way we can do it. Okay.
And then for delta K over K observed, K 100% is basically K observed, and then K 20% is just going to be the highest point and the lowest point. Is that right?
Yeah, K 20% is, for example, here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, right? So if I have, like, for example, 10 points on the curve, and if I fit a line to it, which actually here you see the slope of this curve is 3.4492. So this is K observed for 100% of data, all the data, all the 10 points. Just consider 20% of this data. So what is 20% of this data? Only 2 points, right? 2 points out of 10 points, right?
Yep.
So if you just consider 2 points, so just randomly pick some points, drop them, and just pick 2 points and fit a line to that, okay? That line has a different slope than 3.4492. You can try it on Excel. That line has a different error. And if all the points, in this case, the points are perfectly on a line, right? So in that case, when you just pick 2 points, K 20% is not very different from K 100%. So even if you take 2 points out of 10 and fit a line, your slope is going to be, for example, 3.4, and then you have a different in this third digit, 5, like for example, 6.2. Right? So your error is like 1%, 2%, which makes sense because all your points are clustered on the line, right? Or exactly on the line. But if your data are kind of like scattered, they're not on the line, then a delta K or K observed become larger. Because if you only take 2 points in this scattered data and fit a line, the slope will change significantly, right? So for delta K or K observed, you have to make 2 regressions. One regression, the slope gives you K observed 100%. The other regression, the slope gives you K 20%. And then you subtract these two, take the absolute value, divided by K 100% to get delta K over K observed. Any other question? Let's go back to Zoom. All right. Let's see here. All right. So if you don't have further question, I want to close the class right here. When I get the recording, because after like 20 minutes after I get the email from Canvas that your recording is available. So after I get that link, then I'm going to upload it on YouTube and I'll share it with you. I know one of the students had he needs to do military duty, so he's kind of like he can use that material to, you know, learn it offline. And then again, if you have questions, please send me emails. If you need a Zoom session for like practice, question answer, send me email. And we are going to meet again tomorrow and also Friday. Unfortunately, we have to meet a little bit more because we only, as I said, for this semester, we only had 5 weeks. So tomorrow I'm going to talk about shear stress and, you know, the stress related to Hooke's law. And tonight, please do not stop practicing. Tonight, practice shear moment diagrams. Just tonight, don't leave it for tomorrow, because tomorrow I'm going to teach more materials, okay? Different topics. So practice shear moment diagram. I'm going to put a link to the videos I recorded last semester for shear moment diagrams. And I'll see you tomorrow, okay? Bye.